Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water, or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand-woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Every year, over 150 million cubic meters of plywood are produced worldwide, a volume that could circle the Earth several times in train cars. But few people stop to think that behind this lies a unique technology where wood is literally unrolled into a continuous ribbon and then assembled into a super strong material that can withstand colossal loads. How do ordinary logs, after spa treatments in giant pools and a dance with knives, turn into perfectly smooth sheets ready to serve in furniture, ships, and even skyscrapers? Watch until the end, and you'll discover one hidden secret of this production that isn't talked about publicly. It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, pine, or other species. After being delivered to the factory, the logs go through the first and very important stage of preparation hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours and sometimes up to a day. This sort of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible, as cold wood would simply crumble and break. After their bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface. Then the logs are sawn into standard lengths, ready for the main stage of transformation. The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens, something that contradicts our usual understanding of wood processing. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife, installed parallel to the axis of rotation, is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon, just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk, like a scroll of ancient papyrus, turning a 3-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength and stability of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor, while hot air intensely blows on them from all sides. The temperature and speed of the air are strictly controlled to dry the veneer evenly and avoid cracking or warping. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks, ready for gluing. At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, usually based on phenol formaldehyde or urea resins, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table. On top of it, a sheet coated with glue is placed. And here lies the main secret. Each subsequent sheet of veneer is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, the third's lengthwise again, and so on. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split along the grain and evenly distributes the load over the entire area of the sheet. That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical, and the outer layers have the same grain direction. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-level structure, between whose plates several dozen future plywood sheets are loaded simultaneously. When the press is loaded, the plates begin to close. With an enormous force, reaching tens of kilograms per square centimeter, the plates compress the veneer layups, turning them into dense, thin blocks. At the same time, the plates are heated to a temperature of 302 degrees Fahrenheit. Under the influence of high pressure and temperature, the glue polymerizes, penetrating into the pores of the wood and permanently bonding the layers into a single, incredibly strong monolith. The pressing process lasts for several minutes, after which a finished plywood board is born. Hot sheets of plywood come out from under the press and are stacked for gradual cooling. This is important to avoid internal stresses in the material. After cooling, the sheets undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth and even. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, cracks, glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a corresponding marking is applied to it. The finished, sorted, and packaged stacks of plywood are sent to the warehouse, to later become part of furniture, houses, ships, and countless other structures, demonstrating to the whole world how human intellect can improve upon nature itself. The global scale of production is also impressive. Annually, over 150 million cubic meters of plywood are produced worldwide. If you were to load all of this quantity into railway cars, the resulting train would circle our planet at the equator several times. The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material for which there are several clearly defined paths. Its future fate depends on the thickness and quality of the wood. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets. The largest gasoline production plant in the United States is Marathon Petroleum's facility in Galveston Bay, Texas. It's a true giant, processing 631,000 barrels of crude oil every day. That's about 26.5 million gallons every single day, a staggering number. Let's dive into the atmosphere of oil refining production. It all began long before the era of hybrids, electric cars, and climate summits. Back in the days when America was still smoking and roaring, the world needed fuel, and Texas provided it by the spoonful. On the coast of the Gulf of Mexico, in the Texas city of Texas City, a decision was made back in 1931 to build a plant that would refine oil into liquids that make cars and airplanes roar. By 1933, the plant was operational. At that time, it belonged to Republic Oil, and a little later, it was taken over by Amoco, which eventually became part of British Petroleum. Those were wild times. Every day, a new record. Gallons of gasoline flowed like a river, and the plant gradually expanded. It survived World War II, the oil crises of the 70s, and even an explosion in 2005 when 15 workers died at a neighboring facility, a tragedy that forced a complete overhaul of safety in the entire oil refining region. Have you heard about it? And so, in 2013, the giant changes hands. Marathon Petroleum Corporation buys the plant. And they don't just buy it, they integrate it with their own refinery located nearby. Thus, a single gigantic system is born, the Galveston Bay Refinery, which since then has been processing over 630,000 barrels of crude oil every day. To imagine the scale, that's over 26 million gallons of fuel per day, and the complex covers nearly 1,000 acres. Over 1,500 people work there, not counting contractors and specialists who service the units. It's like a small industrial city, only instead of coffee shops, there are reactors instead of fountains, cooling towers, and instead of a park, thousands of pipelines. Galveston Bay is the pulse of the US fuel infrastructure. It operates 24 hours a day, 7 days a week, without stops or breaks. It's not just gasoline that's born here, they also produce jet fuel, diesel, fuel oil, petroleum coke, and even propylene for the chemical industry. Everything that can flow, burn, and work is squeezed out of every drop of crude oil. Interestingly, the plant's location is strategic. The nearby port allows for receiving tankers from all over the world and a network of pipelines and railways for sending products all over America. Roughly speaking, if you're filling up your tank somewhere in the US, there's a chance that at least a drop of that fuel passed through the furnaces of Galveston Bay. And although the world is changing today, and green energy is being talked about from every microphone, the Galveston Bay Refinery is not giving up its position. Marathon Petroleum is investing hundreds of millions of dollars in modernization, filtration, and reducing harmful emissions. Because as long as the planet is still roaring with engines, this Texas giant remains at the heart of the American highway. We are heading to a territory where it doesn't smell of flowers, but where pipes roar, signal lights flash, and black gold is turned into gasoline. Galveston Bay Refinery, one of the largest plants in the US, and production there begins not with the push of a start button, but with thousands of miles of logistics, pressure, and thermal alchemy. The first drop of oil in this story doesn't yet have the smell of gasoline. It's in its raw form, viscous, dark, with impurities, water, sulfur, and metals. It's delivered by tankers through the port of Texas City, or pumped through pipelines that stretch for thousands of kilometers. This plant can receive over 1 million barrels of crude oil per week. That's an insane amount. The oil goes into huge tanks, so-called crude tanks. Each such tank can hold 500,000 barrels. Imagine that, that's more than 20 million gallons. Here it is stored for several days, where it settles and is heated to a temperature of about 140 degrees Fahrenheit to reduce viscosity and facilitate pumping. Next, the oil goes through desalters. These are special units that remove water, salts, and mechanical impurities. Because salts are death to metal reactors, they cause corrosion and form dangerous deposits. Here, the oil is mixed with fresh water and electrical energy, creating an emulsion that forces the impurities to separate. This is, essentially, industrial cleaning. After this, the main stage, the atmospheric distillation unit. A tower 230 feet high, where oil heated to 650 degrees Fahrenheit is fed in, and vapors rise to the top. And here the magic begins. Heavy fractions like diesel, kerosene, and fuel oil settle at the bottom, while lighter ones, the gasoline fraction, naphtha for petrochemicals, rise to the top. You can imagine this tower as an oil elevator, where each floor is a separate product. The temperature in the column plays a key role. At each height, its own condensation point. Heavy components stop faster, light ones fly further. All this works in real time with control over every degree and every drop. But no, this isn't gasoline yet. What has been collected are raw fractions that are then sent to other units. Vacuum distillation, catalytic cracking, hydrotreating, and only then to blending. That is, mixing to meet the standards for gasoline, diesel, and jet fuel. By the way, gasoline itself is not a single component, but a mixture of dozens of fractions that are chemically and physically stitched together into a precisely calibrated formula, with an octane number, ignition temperature, volatility, aromatics, all according to standard. But let's go back. After the atmospheric tower, many heavy fractions are sent to a vacuum column, where they are distilled under reduced pressure, so as not to burn them to a crisp. From there come components for lubricants, bitumen, and even raw material for plastics. Then even deeper, catalytic cracking, where molecules are literally broken into smaller ones, turning heavy fuel oil into light gasoline. And only when this black magic is complete does the collection of fractions, mixing, adding additives begin, and at the end, storage tanks with the finished product, which again await tankers, pipelines, and rail cars. After all the formidable reactors, furnaces, and towers, where crude oil has been given a good heating, the crucial stage arrives: final blending. This is no longer a turbulent boiling or flowing in pipes. It's like a chemical kitchen, where a complex dish with a taste of power and precision is prepared from a few simple ingredients. Each fraction obtained from previous processes has its own properties. One is light, volatile, with a low octane number. Another is heavier, dense, resistant to temperatures and pressure. From these, like from puzzle pieces, petrochemical technologists assemble the required mixture. This is called blending. And this is the moment when gasoline essentially is born. It is not mixed randomly. Everything happens according to precisely calculated formulas. The fractions are fed into mixing tanks, where every drop is controlled by automation. Machines know exactly how much of what to supply to get the desired grade of gasoline at the output, with a certain octane number, resistance to detonation, and stability during storage. But even the most precise mixing is not the end. Special additives are added to the gasoline composition. These are small in volume, but powerful in effect substances. It is they that help the fuel work better, not destroy engines, not rust in tanks, not evaporate too quickly, not clog injectors, not pollute the atmosphere. Additives are introduced in microscopic doses, literally a few ounces per gallon, but modern fuel is impossible without them. When everything is ready, the gasoline goes into finishing tanks. These are giant steel containers located next to railway lines, truck ramps, and port pipelines. There, the fuel can be stored for days or weeks, waiting for its time. Then, shipment, tankers, rail cars, barges. And so, the fuel hits the road. Maybe this very batch of gasoline will be hissing in the tank of your car in a few days. Maybe it will power a combine, a truck, a boat, or an airplane. But whatever the case, this gasoline has come a long way. From dark, raw mud to perfect, transparent fuel. It is clean, stable, ready to burn, but only when you say, "Start your engine." Every hour, over 100,000 airplanes take off around the world, but only one of them is a true ghost of the sky. It has no tail, leaves no trace on radars, and costs more than gold. The creation of the B-2 Spirit cost the United States $60 billion, and over 40,000 specialists from 600 companies worked on each unit. Its assembly took more than a year, with special hangars, laser-like surgical precision, and materials you can't buy in any store. But what this plane hides is still a secret. And if you watch until the end, you'll find out what it was really created for. The design of the B-2 Spirit strategic bomber began in 1979, when the Cold War was reaching its peak. It was then that the United States Department of Defense initiated the Advanced Technology Bomber program, with the goal of creating a new generation aircraft, capable of penetrating the most advanced Soviet air defense systems while remaining invisible to radars, and delivering nuclear or conventional weapons over intercontinental distances. Leading American aerospace corporations participated in the competition: Northrop, Boeing, Lockheed, and Rockwell. After a lengthy stage of development and testing, in October 1971, the Northrop-Boeing consortium was declared the winner. It was their project that received the designation B-2 and the name Spirit. Unlike previous strategic bombers, the B-2 was built on a unique flying wing design, which provided a minimal radar cross-section and significantly better flight characteristics. In the mid-1980s, the B-2's design had to be significantly changed. The mission profile was adapted for low-altitude flights with terrain following, which allowed for even more effective penetration of Soviet air defenses. This led to a 2-year delay in its first flight and an increase in the program's cost by $1 billion. By 1989, about $23 billion had been spent on the B-2's development, and even specialists from the Massachusetts Institute of Technology were involved in the work, assessing the aircraft's effectiveness under conditions of strict secrecy. The first public showing of the B-2 Spirit took place on November 22, 1988 at Plant 42 in Palmdale, California, which is where it was assembled. The first flight of the B-2 took place on July 17, 1989. Initially, the United States Air Force planned to order 132 aircraft, but after the end of the Cold War and the collapse of the USSR, as well as due to the extremely high cost, the series was reduced first to 75 and then to 21 units, including a prototype, 5 pre-production, and 15 production machines. Almost all B-2s received their own names in honor of American states, emphasizing their uniqueness and symbolic significance for the country. Thus, the B-2 Spirit became not only a technological breakthrough, but also a symbol of American military might at the turn of the 20th and 21st centuries. The production of the B-2 Spirit began not with the manufacturing of individual parts, but with the creation of a completely new industrial ecosystem capable of meeting the unique requirements for technology, materials, and assembly precision. The first and most important stage was the organization of the production base and the development of tools that did not exist before. After the design phase was completed, Northrop Grumman, as the prime contractor, invested over $1,200,000 in creating a specialized integrated composites center in Pico Rivera, California. For this, a former Ford auto plant was repurposed, turning it into one of the world's largest composite manufacturing centers. The production of the B2 required the development of not only new materials, but also special tools, software, testing laboratories, and automated production systems. At this stage, the following were created: unique molds and tooling for forming large composite panels, automated lines for laying carbon fiber, computerized systems for cutting and shaping parts, and autoclaves for heat-treating composites at a temperature of about 350 degrees Fahrenheit and a pressure of 100 psi. The production of the B2 began with digital modeling. Engineers created three-dimensional CAD models and then directly manufactured production tools from them, bypassing traditional mock-ups. This allowed for achieving unprecedented accuracy. Even microscopic deviations could affect the aircraft's stealth characteristics. In parallel, a complex network of contractors and suppliers was formed. Over 6,000 companies and 40,000 workers from 46 states of the United States were involved in manufacturing components. Boeing was responsible for manufacturing the outer wing sections, Vought aircraft, for numerous composite elements, Hughes, for radar systems, and General Electric, for the engines. Only after the creation of this entire infrastructure did the direct manufacturing of parts, their processing, quality control, and subsequent assembly of the aircraft at the main plant in Palmdale, California, begin. Thus, the production of the B2 Spirit started with large-scale preparation of the production environment, engineering innovations, and the development of new technologies, which made the creation of this unique aircraft possible. After the large-scale preparation of the production base, the creation of unique tools, and the establishment of material supply chains, the direct manufacturing process of the B2 Spirit began. Events then unfolded in several key stages, each requiring engineering precision and strict coordination among thousands of specialists and hundreds of contractors. Manufacturing of the main fuselage and wing sections. The manufacturing of the main fuselage and wing sections of the B2 Spirit began with the production of the world's largest composite aviation parts at that time. The central part with the crew cabin was manufactured by Northrop Grumman, while Boeing made the 65-foot-long outer wing sections and the 50-foot-long aft section. The slightest deviations could affect the B2's radar cross-section. In total, over 10,000 composite components were manufactured for one aircraft, using the latest automation and quality control technologies of that time. The precision assembly of the B2 Spirit is a true engineering feat that unfolded in huge hangars, specially created for this project. The assembly of the main sections took place on massive jigs, special platforms that occupied an area comparable to a football field. Here, hundreds of engineers, assemblers, and quality controllers worked simultaneously, each responsible for their narrow stage. Thanks to three-dimensional CAD modeling, all parts fit together perfectly. During assembly, laser measurement systems were used, which allowed for tracking accuracy down to thousandths of an inch. Even microscopic deviations could disrupt the aerodynamics or reduce the effectiveness of the stealth coating. Every joint seam was checked several times, and after connecting the sections, it was manually sealed with special materials to ensure airtightness and invisibility. The scale of the assembly was impressive. Just the central fuselage section required over 1,000 hours of labor, and the total assembly cycle for one aircraft took more than a year. All stages were accompanied by multi-level quality control, from geometry to electromagnetic compatibility. It was thanks to such attention to detail that the B2 Spirit became a benchmark of precision and technological excellence in world aviation. After assembling the main structure, the integration of systems began. Electronics, hydraulics, fuel tanks, engines, flight control systems, radar complexes, and so on. Many subsystems had to be redesigned and adapted to the unique requirements of the stealth architecture. For example, placing the engines inside the wing to reduce infrared radiation. One of the most complex stages was the application of a multi-layer radar-absorbent coating. The process took place in special hangars with a controlled microclimate. Each layer was applied by hand and then checked for defects that could increase radar cross-section. After completing the assembly and integration of all systems, the aircraft underwent multi-level tests, static and dynamic structural tests, checks of all systems operation, flight tests in various modes, and special radar cross-section tests. Any identified deficiencies were eliminated, and individual nodes could be reworked or even manufactured anew. After all tests were completed, the aircraft was officially handed over to the United States Air Force. In parallel, crews were trained, undergoing specialized training on simulators and in real flights. After the production of the B-2 Spirit ended in 2000, these unique aircraft did not become museum exhibits. On the contrary, they remain at the forefront of technological progress thanks to constant improvement. The US Air Force is investing billions of dollars in modernizing each of the existing B-2s to ensure they meet current and future challenges. One of the main areas of modernization is updating the onboard control systems. Outdated analog instruments are gradually being replaced with modern digital interfaces, which increases reliability, convenience for the crew, and allows for the quick integration of new functions. The crew cabin has been equipped with multifunctional displays, and the flight control system has received new software that provides even greater stability and precision in controlling the flying wing. Every year, millions of tons of refractory bricks are produced worldwide, a material capable of withstanding temperatures over 1,500 degrees Celsius and protecting structures where metal melts or flames erupt. Just to line one blast furnace requires up to 4,000 tons of this stone that fears no fire. But what gives it such strength? Why would metallurgical giants, cement plants, and glass furnaces grind to a halt without it? And most importantly, what technological secret turns ordinary clay into armor against flames? Watch until the end, and you'll find out what they don't write in textbooks. At the heart of it all lies not ordinary red clay, which is used for building bricks, but its special variety, refractory or kaolin clay. Its uniqueness lies in its chemical composition, where two oxides dominate, aluminum oxide and silicon dioxide. It is their high content and the correct ratio that give the raw material its main property, an extremely high melting point. To give the future product stability and predictability, manufacturers resort to a technological trick. Part of the mined clay is not sent directly into production, but is first fired in kilns at temperatures up to 1,500 degrees Celsius. As a result of this process, the clay loses its plasticity, sinters, and turns into a very strong, stone-like material called chamotte. This finished chamotte is then crushed and used as the main component, with a certain amount of fresh, plastic clay added to it, which acts as a binder. This approach solves a key problem. It significantly reduces the shrinkage of the products during final drying and firing, preventing deformations and cracking. So, the process begins with the preparation of components. The mined clay and other rocks, as well as the pre-prepared chamotte, are sent to the crushing line. Giant crusher jaws break large pieces, and then roller and ball mills relentlessly grind them into a fine powder with a clearly defined grain size. Control of the fractional composition is extremely important because the future density, and consequently, the strength and thermal conductivity of the brick depend on how tightly particles of different sizes can pack together. After crushing, automated dosing systems weigh each component, chamotte powder, clay powder, water, and other possible additives, with computer precision according to the recipe for a specific type of refractory. This entire mixture is sent to powerful mixers, where it is intensively mixed until a completely homogeneous mass, known as the batch, is formed. Next, the formless mass must acquire its shape. The most common method is semi-dry pressing. The batch, containing a minimal amount of moisture, is loaded into high-strength metal molds. Then, a press exerts an enormous force, measured in hundreds of tons on it, pressing the mass into a steel die. Thanks to this colossal pressure, the particles get as close as possible, displacing air, and at the output, we get a dense, smooth block with perfect geometry. A green brick. Although it already has its shape, it is still very fragile and not resistant to moisture. The next stage requires not strength, but patience and precision. The green bricks are carefully placed on kiln cars and sent to long tunnel dryers. This is a slow and delicate stage, which can last from 1 to several days. Inside the dryer, a carefully controlled microclimate is maintained. The temperature is gradually increased, and the humidity is reduced. It is important that the moisture leaves the brick as evenly as possible from its entire thickness. Any rush or violation of the regime will lead to the outer layers drying faster than the inner ones, which will create critical internal stresses and simply tear the brick apart with cracks from the inside. When all the physically bound water is removed, the culmination of the entire production cycle begins: firing. The brick enters the fiery tunnel of the kiln, where a true rebirth awaits it. Slowly moving through different zones of the kiln, it is gradually heated to peak temperatures, which for chamotte brick are 1,400 degrees Celsius, 100 degrees Celsius, and for high alumina types can exceed 1,750 degrees Celsius. This is not just drying, it is a deep metamorphosis. At such temperatures, complex chemical reactions are triggered, mineral particles soften on the surface and sinter together, forming a strong and dense ceramic structure. In the system of aluminum oxide and silicon dioxide, new crystalline compounds are formed. In particular, needle-like crystals of mullite, which, like reinforcement, permeate the entire structure of the brick, giving it exceptional strength and thermal stability. Having passed the peak of heating, the brick just as slowly passes through the cooling zone. This stage is no less important, as rapid cooling would cause thermal shock and destroy the product that has just gained strength. At the exit of the kiln, a completely new product appears. A hard, ringing, slightly rough to the touch block that is not afraid of fire. Next, only inspection. Each product undergoes a rigorous inspection for compliance with geometric dimensions and the absence of defects, after which it is marked, packaged, and sent to fulfill its main mission: to contain the flame. To realize the true significance of refractory bricks, it is worth looking at the language of numbers. The global market for refractory materials is an industry valued at over 30 billion euros annually, and over 70% of this entire colossal mass of products is consumed by one industry: ferrous metallurgy. Just for the internal protective lining of one large blast furnace, it can take from 2,000 to 4,000 tons of refractories, and one steel teaming ladle, which transports hundreds of tons of liquid metal, eats up several sets of lining per year. A standard chamotte brick of grade SHA5, which is the most common, weighs about 3.5 kilograms and is capable of withstanding temperatures up to 1,690 degrees Celsius. On an industrial scale, this means that millions of tons of these bricks stand guard annually, containing thermal energy equivalent to the energy of thousands of volcanoes. The field of application of refractory bricks is as wide as the hot processes that form the basis of our civilization. Its main consumer is, without a doubt, metallurgy. Here, it is absolutely indispensable. Refractory bricks are used to line the inside of blast furnaces, where pig iron is born from ore. They are used to line oxygen converters and electric arc furnaces, where pig iron is transformed into steel. Huge steel teaming ladles that transport molten metal are also protected on the inside with a lining of refractories. Moreover, for each zone of the unit, its own special type of brick is selected, capable of withstanding not only temperature, but also the chemical aggression of the melt and slag. The second most important consumer is the cement industry. Long, several hundred meter long rotary kilns, in which cement clinker is fired at a temperature of 1,450 degrees Celsius, are completely lined on the inside with special types of refractory bricks. Without this protection, the steel shell of the kiln would burn through in a matter of minutes. The glass industry also cannot exist without refractories, huge tank furnaces, where the glass mass is melted at a temperature of about 1,600 degrees Celsius, are lined with special, very resistant types of bricks that can withstand not only the heat, but also the aggressive chemical effects of molten glass for years. Besides these giants, refractory bricks are used in the thermal power industry for lining boilers and furnaces, in the chemical and oil refining industries for lining reactors, and in waste incineration furnaces. And of course, on a much smaller scale, we encounter it in everyday life. It is from chamotte brick that fireplaces, stoves, and chimneys are built, as it guarantees safety and durability, reliably containing the heat in the heart of our home. Every year, over 100 million small arms are produced worldwide. But only one rifle has truly become a legend: the AK-47, a symbol of simplicity, reliability, and an incredible history. It can be assembled and disassembled in minutes, even in the harshest conditions. And that's precisely why it earned the nickname, the weapon that never fails. In this video, we'll take a first-time look behind the scenes of its production, from a raw steel blank to the final tests at the shooting range. You will see the hidden processes that are usually not shown, and you will understand why the AK-47 has become the most recognizable rifle on the planet. When I entered the factory, I immediately felt that I had stepped into a place with a huge history. The air smelled of metal and oil everywhere, and the sounds of working machines created an atmosphere of important work. In this video, I want to show you how the AK-47 is made, starting from the raw materials and ending with the final assembly. We will see how a rifle, known worldwide for its reliability and simplicity, is born from ordinary materials. Believe me, you won't want to miss this exclusive look at the production process. On the production floor, I noticed how ancient methods are combined with modern technologies. Here, they strive to preserve traditions, but also make the process as efficient as possible. Next to the forging areas stood modern machines controlled by computers. The craftsmen here don't just work with metal. They put their soul into every detail, turning it into a part of a legendary weapon. It seems that every corner of this factory is steeped in history and the pursuit of perfection. The manufacturing of barrels is one of the most important and complex stages. The barrel is the heart of the rifle, and its accuracy is very important. I saw how large metal blanks are turned into hollow tubes with the help of special machines. But the real magic happens later, when spiral grooves are cut inside the barrel. These grooves help the bullet to spin so it flies more accurately. This is a very complex process, requiring enormous precision. Even a small mistake can ruin everything, so attention to detail here is at the highest level. I saw how the masters perform this work with pride and responsibility. Each barrel undergoes numerous checks to ensure it meets all standards. Engineers use special instruments to measure and check the inner surface of the barrel. It really looks like a scientific investigation, because even the slightest defect can affect the accuracy of a shot. They check the barrels with ultrasound, measure the diameter, and look for cracks. All this is done to make every rifle as reliable as possible. At the factory, they use both old methods and new technologies. For example, the stocks for the rifles are still made by hand from wood. The masters choose the best wood, birch or walnut, and process it to be strong and durable. They sand the stocks and cover them with special compounds to make them look beautiful and be strong. This shows that traditions and respect for history are very important here. At the same time, for modern models, polymers are used, which make the rifle lighter and more convenient. Injection molding machines produce plastic stocks with high precision, which helps to reduce weight and improve the weapon's characteristics. This combination of old and new makes the AK-47 truly unique. Quality control is a very important part of the work at the factory. Every detail goes through numerous checks. This is not just a visual inspection, but a real process using ultrasonic tests and magnetic particle inspection. All this is necessary to ensure that there are no defects in the parts that could affect the weapon's performance. Every assembled rifle is checked at a special shooting range to ensure it shoots accurately and reliably. I stood behind protective glass and watched as engineers tested each rifle. First, they checked how all the mechanisms worked, and then they conducted a test firing. This is very important, because even a small problem can cause the weapon to fail at a critical moment. If something goes wrong, the rifle is sent back for rework. Engineers also collect data from the tests to understand what can be improved in the production process. One of the engineers told me that all test results are recorded and analyzed. This allows for continuous improvement of the quality and reliability of the weapon. This process never stops. Every employee at the factory tries to do their part as well as possible. I was amazed that they don't just follow instructions here, but constantly strive to improve every detail, making the AK-47 even better. Applying a protective coating is another important stage of production. This helps to make the weapon durable and protected from external influences. At the factory, they use different coatings: traditional bluing, which makes the metal black and matte, and modern coatings that protect against rust. I watched as workers applied these coatings, and it was clear that they do it with great attention to detail. This is another example of how old and new methods are combined here to create the best weapon. The factory also makes magazines for the rifles. Magazines are an important part of any rifle, and they are given a lot of attention here. They make magazines from durable materials to withstand great loads. Each magazine is checked to ensure that it works reliably and will not fail in combat. I saw engineers inserting magazines into the rifle and checking the feeding of cartridges. This is another important stage that shows how they approach quality here. The most impressive stage is the final testing. In a special shooting range, each rifle is checked by firing it. I stood behind bulletproof glass and watched as engineers fired the rifles, testing them for durability and accuracy. Each rifle goes through a series of tests: single shots, automatic fire, and testing in different conditions. If something goes wrong, the rifle is sent for rework. Engineers collect data from these tests to understand how to improve the weapon. This is a continuous process that helps to make the AK-47 so reliable. When I was leaving the factory, I couldn't stop thinking about the complex history of this weapon. On the one hand, it has become a symbol of struggle and revolutions, and on the other hand, it has been used in wars and destruction. Having seen how much labor and skill is invested in each rifle, I realized that this is not just a weapon, but the result of engineering talent and human labor. Every detail is created with great attention, and this makes the AK-47 something more than just a rifle. It is a symbol of history, traditions, and the pursuit of perfection. The AK-47 is not just a weapon, it is a part of history. It was created to be reliable and easy to use. It can be disassembled and assembled in minutes, even in difficult conditions. This makes it popular among military personnel around the world. The simplicity of its design and high reliability are what make the AK-47 so special. Having seen how it is produced, I understood that every detail matters. Every screw, every barrel, and every stock is created with enormous attention to detail. Every year, thousands of combat vehicles are produced worldwide, capable of changing the course of history. In terms of weight, that's hundreds of thousands of tons of steel, aluminum, and composites, transformed into something that has to withstand fire, explosions, and impacts. Imagine armor thickness of over 5.5 inches, an engine with 1,500 horsepower, and a cannon that hits a target from 2.5 miles away. But the most important part isn't the numbers. Hidden inside every tank are technologies that aren't written about in open sources. Watch until the end, and you'll find out what's usually kept behind the closed gates of defense plants. Every painting begins with a sketch, and a tank with a design project. The design must take into account the integration of modern materials, armor, electronic systems, and weaponry. The key materials are high-strength steel, composite materials, aluminum, as well as special armor. First, the hull is planned and manufactured. It's made from high-strength armored steel, which can protect the entire crew from enemy fire. The steel must undergo heat treatment to increase its strength. In some places, the hull is reinforced with composite armor made of special multi-layered materials. Their composition is classified, but it can be ceramics, metal alloys, and plastics. The steel plates are cut using a laser to ensure high-dimensional accuracy. The armor thickness varies depending on the part of the hull. For example, in the front section, it can reach 14 centimeters. The panels are joined by machines, specialized welding robots, which immediately and thoroughly check the seams for strength, as they must withstand great loads and explosive impacts. Then, special modules, protective screens, and mountings for fuel tanks are attached, and it is treated with an anti-corrosion coating. Some tanks are even equipped with reactive armor. The tank's turret is the second most important part, because it handles the fire control functions and contains the main armament. It's made from materials similar to the hull, but with a more complex shape. For the turret, thick armored plates are used, which are bent and stamped by special giant machines to get the precise shape. In some places, the armor thickness can reach 12 centimeters, and with the composite layer, even more. The engine is manufactured separately. The Honeywell AGT 1500 operates on the principle of a gas turbine, almost like the engines of aircraft. It has a power of 1,500 horsepower and can run on various types of fuel. The main materials for the engine are titanium alloys, which are capable of withstanding high temperatures, up to 2,200 degrees Fahrenheit. Also, heat-resistant steel for shafts and combustion chambers, and composite materials for some elements. The rotor blades are cut from titanium plates using laser and water jet systems. The stator parts are also manufactured separately and coated with an anti-corrosion coating. The compressor, which forces air into the combustion chamber, is made of lightweight alloys to ensure high performance. The chamber is made of heat-resistant steel, capable of withstanding temperatures over 2,000 degrees Fahrenheit. Its inner walls are coated with a special ceramic layer to prevent overheating. Each element is checked for its ability to withstand extreme rotations of up to 50,000 revolutions per minute. After manufacturing and checking all the parts, the assembly process begins. The main engine body is assembled from several sections that are connected to the compressor, combustion chamber, and turbine. The shaft connects the turbine to the compressor and ensures the transfer of energy. A cooling system is added to the engine, which uses air and oil to reduce heat during operation. A unique filtration system is also installed, which cleans the air of dust and sand, which is especially important for operation in deserts or steppes. The engine is installed on a test stand, where it is checked for maximum power, temperature regime, and fuel consumption. Tests are conducted for long-term operation under high load. The engine is installed on the tank chassis for testing in real conditions. Its operation is tested on various types of fuel, including jet kerosene and diesel. At this stage, all previously manufactured parts are joined into a single structure. First of all, the engine is installed in the hull along with the transmission. After that, the components of the running gear are added, including tracks, shock absorbers, rollers, and suspension, which allow the tank to withstand high loads on rough terrain. I was shocked by how it all looked. It's just so massive and powerful. During the integration process, special attention is paid to the installation of the turret with all its systems. The turret is mounted on a special bearing ring that ensures its smooth rotation of 360 degrees. After this, A 120mm cannon, stabilization, and aiming systems are integrated into the turret. Thermal imagers, laser rangefinders, night vision devices, and other electronic equipment for the crew are also installed. The fire control systems are connected to a central computer that synchronizes data from all sensors. The ammunition is located in a special compartment with blast-proof panels, which ensures the crew's safety in the event of shell detonation. Next, auxiliary systems are installed, such as the air conditioning system, which ensures the crew's comfort in extreme conditions, as well as systems for protection against weapons of mass destruction. Elements of additional armor, including composite and modular blocks, are added to the hull. For each tank, protection options are individually selected depending on the assigned tasks. The next step is the installation of all electronic systems. All cables are placed in special channels for protection against mechanical damage. Each tank has to go through multiple levels of testing. First of all, the tank is checked for the tightness and strength of the hull. In special chambers, the hull is subjected to high pressure to ensure there are no leaks or cracks. To do this, the hull is filled with compressed air or liquid, and the outer surface is covered with a special solution to detect even the smallest defects. This stage is especially important, as the hull must withstand the pressure of a blast wave and provide protection for the crew. Special attention is paid to checking the running gear. The tank is driven over obstacles that simulate real combat conditions: hills, pits, marshy areas, and sandy roads. On test ranges, the tank overcomes slopes of up to 60 degrees, which allows for checking its stability and maneuverability. The tracks are checked for their ability to withstand constant impacts and friction over a long period of time. The suspension is tested for its ability to soften impacts during high-speed movement. The tank's weapon systems also undergo intensive testing. The 120mm smoothbore cannon is checked for accuracy and stability of firing on the move. For this, targets are set up at various distances on the test range, including targets located at a distance of up to 4,000 meters. In addition to the cannon, machine guns and grenade launchers are checked. An important stage is testing the fire control system, which must accurately synchronize data from the laser rangefinder, thermal imager, and onboard computer. The electronics of the system are tested separately. On special test stands, communication, navigation, and surveillance systems are checked. Special attention is paid to night vision systems to ensure a clear image in complete darkness or a smokescreen. The onboard computer is checked for information processing speed and its ability to operate in extreme conditions, such as high temperature, vibration, and humidity. The final stage is armor testing. On special ranges, the tank's hull is fired upon with various types of weapons: anti-tank missiles, shaped charge projectiles, and grenades. This allows for evaluating the effectiveness of the composite armor and additional protective screens. The armor must stop projectiles and minimize the effects of a blast wave. And only after completing all multi-level checks are the finished machines handed over to the military.